So the species I was given today was MnNO2 3NH3-. So let's get started with the VPT. So what we first need to do is distinguish what the oxidation state is for Mn, and it's going to be 2+ in this case because NO2 has a minus charge and we have 3 and our species is negative. So let's go. Mn is going to reside in the 3d orbital, so we're going to have 1, 2, 3, 4, 5, 5 electrons. Alright. Now, since we have NH3, that's going to be a strong field ligand, and all strong field ligands do is they make the electrons that are in our d orbital pair up. So we're going to first then go down, and we're going to call this pairing energy. And don't forget to label that this is the ground state for this case. Now, we go down to the pairing energy. Okay. And in here, this is where the strong field ligand is going to pair up the electrons. So we're going to have 1, 2, 3, 4, 5 electrons, okay? Now, what we need to do is we need to write that it's an excited state, and then we need to box the orbitals that we're hybridizing. So we're going to call this hybridize, okay? And we're going to come down to the bonded state. And so in the bonded state, let's draw our electrons again. So we're going to have 1, 2, 3, 4, 5 electrons. Okay. Now we need to name the hybridization orbitals. So this is going to be D2sp3, which is an inner d orbital. It's inner because if you can see here, we hybridize the inner d orbital, not the outer d orbital, but the inner. So we're going to call it inner d orbital. Just cut off short. All right. So now let's draw the pairing electrons. So the reason why we're doing little electrons is to show that these electrons are paired. And they're going to be paired with the ligands that we have. So we're going to have 3 sigma NO2s, and we're going to have 3 sigma NH3s. Okay, now it's time to draw the shape. So we're going to have Mn, our metal in the middle. This shape is going to be octahedral, and the reason why we know this is because we have 6 ligands. And we also know this based off of our hybridization, which was D2sp3, which is the hint that we're going to have an octahedral shape. So let's go. We're going to have a line here and a line here. That's going to be our 6 bondings. So we're going to have H3N. The reason why we write it like this is because it's the N, the electrons that are bonded to the Mn, to the central atom. H3N, and then NH3, and then we're gonna have NO2. And the special thing about NO2 is it's a linkage, so it can bond with either the N or the oxygen. So that's very special. Okay. Now looking at this, the coordination number is going to be 6. And the reason why it's 6 is because this central atom has 6, it's shared by 6 ligands. Now, it can also be a bidentate, but we all have monodentates here. These are all monodentate ligands, so we're going to have a coordination number of 6. Alright, now let's look at the CF, or the crystal field diagram. So we're going to have 1, 2, 3, 4, 5 electrons in its 3d orbital. We're then going to split it off into here. This is going to be called the XY, the XZ, and the the YZ. And then down here, or up here, is going to be called the Z squared, and then the Z X squared minus Y squared. And now the interaction between these is that these orbitals do never touch the central atom, Mn in this case, and these ones do. Since we have a strong field ligand, this is going to be a larger splitting energy. Okay, you need to remember that you need to label this bottom one with T2G, and it's easy. This has 3, so T2G, and you have to label this top one with EG. Okay, now let's go and let's fill the electrons. Since this is larger, these electrons don't have enough energy to go all the way up here. So we're just gonna fill the bottom one. 1, 2, 3, 4, 5. Okay. Now let's go and answer these questions. So it's asking one, is it diamagnetic or paramagnetic? And it's going to be paramagnetic because we have lone pair electrons. Two, is it high spin or low spin? In this case, it's going to be low spin. And all this is saying, or all that this means, is that these electrons don't have enough energy to come up, and so they're going to have a lower spin. And the only way that these electrons can ever go up is if they get excited by a particular wavelength of energy that will allow them to go up. This is where you see your different colors, and this is where ligands are kind of special in the sense that with weak field ligands and strong field ligands, you can get just a variety of colors. And so now let's look at three. What's stronger, the pairing energy or the crystal field splitting energy? And in this case, it's going to be the crystal field splitting energy. And this is because we have such a strong ligand and it requires so much energy that we need more energy for this than we do for the pairing electrons. Hopefully you found this helpful and you have a nice day.